All right, welcome back everyone to a new deep dive. And today we're tackling some pretty crucial research, I think. Particularly for those of you who are really into the whole world of AI and Web3 security. We're dissecting the paper. It's called AI Agents in Cryptoland, Practical Attacks and No Silver Bullet.
Ooh, that's a good title.
It is a good title. It's by Atharv Singh Patlin and colleagues. And really, if you are, if you're in the weeds building, deploying AI in decentralized finance.
Yeah, if you're in that world.
Or even if you're just kind of like tracking the cutting edge of what's happening, I think this paper is vital for understanding some of the security concerns.
Yeah, I mean, this paper is so cool because it really shines a light on some real world vulnerabilities that are coming up when you have these autonomous AI agents that are operating within these systems, these blockchain-based financial systems. And in the next few minutes, we're going to really break it down.
Yeah, let's extract those core insights.
Okay, so what they're basically introducing is this idea of context manipulation. As like a significant attack surface. And we're moving beyond like simple prompt injections, right? This is like memory, external data, all of that.
Wow.
They actually provide empirical proof of these attacks on this Eliza OS framework. So like they actually show unauthorized crypto transfers.
No way.
Even when there are defenses in place.
That's scary stuff.
It's a little scary, but I think ultimately what the paper is really emphasizing is this need for a new paradigm. And they call this like fiduciarily responsible AI in finance.
That's a mouthful.
Yeah, it's a lot.
But we're going to unpack it. So let's get into it.
Let's get into it.
Okay, so the paper, it kicks off by talking about this, increasingly powerful combination, right, of AI agents. And, we're talking about those systems that can perceive reason and then actually act.
They do things.
They actually do things in the decentralized world of Web3.
Right.
So what do the authors say is really kind of fueling this convergence?
Well, they rightly point to the fact that LLMs, large language models, are making these huge leaps.
Yeah, they're getting so good.
And, that's giving AI agents much more sophisticated reasoning and decision-making capabilities.
Right, so we're not just talking about like rule-based bots anymore.
No. These things can actually think.
Right.
In a way. And so, coupled with this open, data-rich environment of blockchain, it creates a really fertile ground.
Yeah, it makes sense, right? Like AI needs data to thrive.
Absolutely.
And the blockchain has it.
Yeah, and they can analyze this huge amount of data and use it to inform their actions.
Totally.
It's like a match made in heaven, but also maybe a little bit scary.
Yeah, well, that's the thing, right? We're not just talking hypotheticals here.
Right.
The paper points to ElizaOS, which is an AI 16's DAO framework.
I've heard of that.
As a prime example of this stuff in action.
Yeah.
AI agents are already out there trading crypto, doing all this crazy stuff, engaging on social media.
It's wild.
I know, it's crazy.
And think about this. Eliza S-based agents are actually, right now, managing over $25 million in assets.
So this isn't just theoretical.
This is real money.
Yeah.
This is a live environment.
Real money on the line.
It is.
Which is why, understanding these security flaws is absolutely critical.
Yeah, I mean, if you're in that space, you need to know this stuff.
Absolutely. And what's interesting is the paper even mentions some specific examples.
Oh, yeah?
I think a lot of people might have heard of, like Mark Andreessen, of course, has an agent. And then there's this Deegan Spartan AI.
Yeah, I've seen that one on X.
Yeah, and they're both, kind of like persona emulating investment agents on X. So it's taking what could be very abstract and making it, something you might see in your Twitter feed.
Yeah, it makes it real.
It really does. And that brings us to, I think, the central question that the researchers are tackling here.
Okay.
How secure are these AI agents when they're actually handling these financial transactions on the blockchain?
Yeah, that's the big question.
Because we're talking about, irreversible transactions.
Once it's on the blockchain, it's there.
It's done, yes. So the stakes are as high as they get.
Yeah, and I think that's the crux of it, right?
Yeah.
If one of these AI agents makes a bad decision, a harmful financial decision because it's been manipulated, there's no safety net.
Right.
And I think the paper makes a really good point, which is that while we've seen research on LLM vulnerabilities and AI agent security in general, there's a big gap when it comes to these unique risks that you get when you put AI agents in finance on the blockchain.
And that's exactly what this paper is aiming to fill, right? This gap.
Right. That's what they're trying to do.
They're saying, look, we need to look at this because...
a whole other beast.
It is. It is, because you have the autonomy of the AI, but then you also have that finality of the blockchain transaction.
It's scary.
And so you have to think about it in a different way.
It's a unique set of security challenges, that's for sure.
It is.
So let's dive into this attack vector. They introduce context manipulation.
Okay.
What is that? What are the key elements of this? It sounds like a pretty broad umbrella.
You're right. It is a very comprehensive way of thinking about attacks.
Okay.
So they define context manipulation as any attack that basically targets these different context surfaces that an AI agent relies on to actually operate. So this is like, the initial input, a prompt, but then also their memory systems and any external data feeds they might be bringing in.
So it's not just like a one-time trick.
No.
It's like you're influencing its entire understanding of what's going on.
Yeah, exactly.
And its decision-making.
Over potentially a long period of time.
That's scary.
It's a long game.
Yeah.
And what's really interesting is that they frame this as generalization of some of the attack methods that I think people who are in this space are probably already thinking about.
Like what?
So direct and indirect prompt injection are actually subsets of this much broader context manipulation.
Oh, so this is like the big umbrella.
It is, yeah.
And then those are more specific types.
Right. So instead of just think about how do I craft the perfect malicious prompt,
right,
we have to think about all of the ways an attacker could be.
Get in there.
Yeah, get in there and start messing with the information the agent's using.
Yeah, like the entire context.
The whole thing.
That the agent is operating in.
Yeah, and then they highlight this new threat, which I think is especially concerning.
Oh no, what is it?
It's called a memory injection attack.
Memory injection attack, okay.
And this is particularly relevant for agents that use shared memory.
Oh, right, because a lot of these agents they keep track of past interactions.
Exactly.
Yeah, okay, so how does memory injection work?
So imagine you have this AI agent. It's keeping a history of all its past interactions, right? An attacker could figure out a way to inject malicious instructions into that stored memory.
Oh, wow.
And then later on, the agent's going to be going about its business.
Right.
And it pulls up that corrupted memory and it just acts on it. And there's no prompt at that point.
It's like a sleeper agent.
It is, yeah.
So even if you have like good defenses against prompt injection, if you've got bad information lurking in the memory,
doesn't matter.
It can still get you.
Right. And that's a huge part of their argument. And I think it's a really crucial takeaway for anyone listening is that those basic prompt-based security measures, they're just not enough.
Not good enough.
Because once you can corrupt that stored context, it can lead to all these cascading vulnerabilities.
It spreads.
Across multiple interactions, even different platforms.
It's a nightmare.
It's a total nightmare.
Okay, so they actually put this into practice, right?
They used the Aliso S Framework to actually validate this.
Okay, cool.
So ElizaOS, as we've discussed, it's this decentralized AI agent framework that's designed to automate different Web3 operations. And the researchers were actually able to show that it is vulnerable to these direct prompt injection attacks.
Oh, wow.
And that resulted in unauthorized crypto transfers?
Like real crypto transfers?
Yeah, so even just a carefully constructed prompt could trick it into sending crypto to the wrong place.
That's pretty alarming.
It is. But what's even more concerning, and this is really what makes this paper so groundbreaking, is that they showed even the state-of-the-art prompt-based defenses.
Like the best defenses out there.
The best stuff that's out there right now could not prevent these memory injection attacks.
Oh, wow.
And that really kind of highlights, I think, how inadequate our current mitigation strategies are.
Yeah, we're not ready for this.
We're not ready for this.
So they gave this really cool example of this cross-platform memory injection. With Melissa on Discord and Bob on X.
Yes. Can you walk us through that? Because I think that really brings it home.
Okay, so picture this. They outline this scenario. In figure 1 of the paper, there's this attacker, Melissa.
Right.
And she's interacting with an ElizaOS agent on Discord.
Okay.
And through this interaction, she manages to inject these malicious instructions into the conversation history that the agent is storing.
Okay.
Now, the agent might only respond to the last seemingly harmless part of Melissa's input.
Right.
But remember, it's saving the whole exchange.
The whole thing.
Including the bad stuff.
Right.
So then later on, Bob, a completely legitimate user, he comes along and interacts with the same ElizaOS agent, but this time on X. And he asks it to do something standard, like transfer some ETH.
Right.
But because ElizaOS is sharing its memory across platforms and users, when it goes to retrieve its past interactions to figure out what to do, it pulls in the malicious instructions that Melissa planted way back on Discord. And so instead of sending Bob's ETH where it's supposed to go, it ends up going to the attacker's address.
That's bad.
That's bad.
That's really bad.
And that just shows you how these vulnerabilities can propagate. Like something happens on one platform can have consequences on a completely separate platform.
Right. It's like it highlights how interconnected everything is, and then how that could potentially be exploited on a wide scale.
Yeah, if there's a vulnerability in how the memory is managed and accessed, it can have these cascading effects.
Across the whole ecosystem.
The whole thing.
Yeah, it's a big deal.
All right, so before we go deeper into the ElizaOS experiments, let's talk a little bit about the background on this, because the paper provides a good overview of some early AI agents in DeFi. And they mentioned Truth Terminal.
Yeah, Truth Terminal. What an interesting project.
It was kind of a pioneer in this space.
It was.
And it was designed to operate autonomously within DeFi. And it used this really interesting multi-signature wallet system.
Oh, tell me about that.
Yeah, so basically, for any transaction to go through, it needed approval from a council.
Okay.
So it was kind of like an early attempt at security through consensus.
Okay, interesting.
Yeah, and it made its investment decisions by analyzing real-time data.
So it was really like plugged into the market.
Totally, yeah.
Interesting.
And it was even really active in engaging with the crypto community on social media.
I vaguely remember that.
Yeah, and it actually gained a lot of attention for that.
Really?
Yeah, it was known for these humorous and sometimes philosophical posts on X, which got it a lot of followers.
Interesting. So it was kind of like building a personality.
Totally.
Yeah. And did it get any funding?
Yeah, it actually did.
Wow.
Mark Andreessen gave it a $50,000 Bitcoin grant. Yeah, which was really a sign of support for this whole idea of autonomous agents in the crypto space.
That's huge.
It was. And by December 2024, its portfolio had grown to something like $37.5 million.
So it was actually doing pretty well.
It was, which shows you the potential, but also the stakes, right?
Yeah, totally.
Because if something goes wrong,
it's a lot of money.
It's a lot of money.
So ElizaOS is kind of like building on the lessons learned from those early projects like Truth Terminal.
That's exactly it. Yeah.
It's interesting.
It was developed by AI16's DAO, and they were drawing on those experiences.
Yeah.
They wanted to make it more flexible so you can do multi-agent simulations, and users can actually deploy their own AI agents for a wider range of tasks.
So it's more customizable.
Exactly. Yeah.
Very cool. And, you know, the paper also talks about these more general vulnerabilities that can affect the language agents, not just the ones operating specifically in DeFi.
Yeah, it's a good point. Like, this is a broader issue.
Right.
So what were some of those?
So they talk about things like backdoor attacks.
Right, where the model itself has been compromised.
Right, so that's like intentionally designed to be malicious.
Right, right.
And then they talked about direct prompt injection, which we already discussed.
Like SQL injection for LLMs.
Exactly. And then indirect prompt injection.
Right, where it's the external data that's compromised.
Yes, so you have to think about all those different vectors.
Yeah. It's a lot for developers to keep in mind.
It is. And so to give people a framework for thinking about this, the paper introduces this idea of a general AI agent framework.
Okay, that makes sense.
Can you kind of outline the core components of that?
Sure. So they break it down into 4 key modules.
Okay.
First, you have the perception layer, which is how the agent gets information from its environment.
So like user prompts.
Yeah, user prompts, API calls.
External data.
Blockchain data, all of that.
Okay.
Then there's the memory system, and that's where the agent stores and retrieves information.
So that would include things like the knowledge base.
Yeah, the knowledge base, history of interaction.
Okay.
And then there's the decision engine.
The brains of the operation.
Exactly.
Yeah.
That's where it analyzes the context and decides what actions to take. And finally, there's the action module, which is responsible for actually executing those decisions.
So that could be like making an API call.
Exactly. Yeah.
Signing a transaction.
Interacting with a smart contract.
Okay. Got it.
So it's like a continuous cycle, right?
Yeah, so the agent is taking in information, processing it, acting, and then updating its internal state based on the outcome.
Exactly. It's always learning and adapting.
So it's like a feedback loop.
Yeah, it's a loop.
So within this framework, the paper really focuses on these safety attacks that happen through context manipulation.
Right, because those are the scariest.
They are. So what are the objectives an attacker might have in mind?
Well, according to the paper, they're usually trying to do one of three things.
Okay.
Either compromise the agent's safety,
okay,
which means making it do something it's not supposed to do.
Like an unauthorized transaction?
Exactly.
Okay.
Or they're trying to disrupt its liveness.
Okay.
Basically causing a denial of service attack.
So it just stops working?
Yeah. It can't function properly.
Got it.
And then the third thing they might try to do is violate the agent's privacy.
Okay.
Like by extracting sensitive information.
Stealing data.
Yeah, but the paper is really focused on safety attacks.
Okay.
Specifically the ones that lead to those unauthorized actions.
Right.
Like making an unauthorized financial transaction.
Yeah, because that's where the real damage can happen.
Exactly. That's where the money is.
So they actually categorize the different ways these attacks can happen, right?
They do, yeah.
What are those?
So the three main categories are context manipulation, which we've been talking about, malicious model deployment, and action space exploitation.
All right, break those down for me.
Okay, so malicious model deployment is when the AI model itself is compromised.
Okay.
Like it was either intentionally designed with vulnerabilities or someone found a way to exploit it.
Got it.
And then action space exploitation is when attackers are trying to abuse the legitimate functions of the agent.
So it's like tricking it into doing something it's allowed to do.
Yeah, but in a harmful way.
Got it. Okay.
But for this paper, they're really focusing on context manipulation.
Right.
And they make some assumptions about the other two categories.
Yeah. Why is that?
Well, they're assuming that the developers who built the agent are acting in good faith.
Okay.
And they've taken some basic security measures to protect the model and define a safe action space.
So they're saying, let's assume that part is handled.
Right. Let's assume that's taken care of.
Okay.
And let's focus on the risks that come from manipulating the context.
Because even with a well-intentioned developer and a well-designed system, there's still that potential for attack.
Exactly. Context manipulation is a very real threat.
Yeah.
And it doesn't require any special access.
Right. You don't have to hack into the system.
Right. You just need to be able to interact with the inputs, the memory, the external data.
Got it. So when they talk about the attacker, they do put some limitations on what they can do, right?
They do. They assume that the attacker's ability to mess with the context is bounded.
Okay.
Which means they can inject some malicious content.
Okay.
But they can't just rewrite everything.
Okay, so they have some power.
Yeah.
But it's limited.
It's not unlimited.
Okay, that makes sense.
Which makes the scenarios more realistic.
Right. So within this idea of bounded capabilities, they break down the different types of attacks. So remind us what those are.
Okay, so we've got direct prompt injection, which is basically embedding malicious instructions within a normal conversation.
Okay.
Like telling a Discord bot to do something it's not supposed to do.
Okay, got it.
And then there's indirect prompt injection.
Yeah.
Where the attacker compromises an external data source. So they might inject malicious instructions into an API response or a blockchain data feed.
So the agent's getting bad information.
Exactly, yeah. And then finally there's memory injection, which is all about modifying the agent's stored memory.
Like it's conversation history?
Yeah, conversation history, it's knowledge base.
Okay.
And they can do this by either getting direct access to the storage or by using those prompt injections to insert fake history.
Yeah. Tricky.
It's tricky stuff.
So what's the difference then between prompt injection and memory injection? It seems like they both kind of do the same thing.
Well, the key difference is really the timing and the persistence of the effect.
Okay.
So prompt injection is all about getting the agent to do something bad right now.
Okay.
Like in the current interaction.
Got it.
Memory injection is more of a long-term strategy.
Okay.
It's like planting a seed.
Right.
You're putting that malicious information in the memory and hoping it'll influence the agent's behavior later on.
Down the road. Down the road, yeah.
So it's like a time bomb.
It kind of is, yeah.
And the paper says memory injection is a lot more severe.
It is.
Why is that?
Well, because once those malicious instructions are in the long-term memory, they can spread to other users.
Oh, wow.
And even across different platforms.
Right, because it's all connected.
Exactly. And because it becomes part of what the agent considers normal, it's much harder to detect.
Yeah, it's not like a one-off thing that stands out.
Oh, it's hidden in there.
It's blended in.
Yeah.
So let's talk more about ElizaOS and how it fits into all of this.
Okay.
First of all, how does its architecture match up with the general AI agent framework?
It's actually a really good match.
Okay.
So in ElizaOS, you have these things called providers and clients that handle communication across platforms.
Okay.
And they basically act as the perception layer.
Right.
They're gathering the data and the user input.
Okay.
And then you have the agent character file,
which defines the agent's personality and behavior.
Okay.
And that's basically the blueprint for the decision engine.
Got it.
And then you have the evaluators and the external databases.
Yeah.
And they store things like the conversation history.
Okay.
That's the memory system. And then finally you have the plugins, which allow the agent to interact with external services.
So like a crypto wallet.
Yeah, like a crypto wallet, web search, and that's the action module.
So it all lines up pretty neatly.
It does, yeah.
Okay, so let's talk about their findings regarding indirect prompt injection in ElizaOS.
Okay.
What did they find?
Well, they found that ElizaOS uses sandboxing to protect sensitive information.
Like private keys?
Yeah, private keys, things like that.
Okay.
But the security around the plugins is a bit weak. Yeah, and that makes it vulnerable to prompt injection attacks that come from external sources.
So like if it browses a malicious website.
Exactly, yeah. And they actually demonstrated this with what they call the strawman attack.
Okay, what did they do?
So they connected ElizaOS to an account on X and gave it access to an Ethereum wallet on the Sepolia testnet.
So this is like a testing environment?
Exactly,
yeah.
And then they crafted a malicious reply to one of the bot's posts. And this reply had a carefully crafted prompt in it that told the agent to transfer some ETH to the attacker's address. And it actually worked.
Oh, way.
ElizaOS parsed that and executed the transaction.
On the testnet?
On the testnet, yeah.
But it wasn't just the testnet, right?
No, unfortunately not.
They did it on the mainnet too?
They did, to really drive the point home.
Oh, wow.
They repeated the experiment on the main Ethereum network with real funds.
And it worked.
And it worked.
Wow.
They actually included the Etherscan transaction details in the paper.
So you can see the proof.
You can see the proof, yeah.
Wow, that's a big deal.
It's a big deal. It shows this is not just theoretical. This is real money that can be stolen.
So what conclusions did they draw from this?
Well, I think the main takeaway is that we need to think differently about security in these systems.
Yeah.
Sandboxing is good, but it's not enough.
Right, because the LLM can still be tricked into using those plugins in a bad way.
And the problem is that the LLM is making decisions based on the input it gets.
Right.
So we need to make sure it can tell the difference between good instructions and bad instructions.
And in this case, with the X plugin, how did the LLM get tricked?
So the X plugin was polling for new replies. And when it found a reply, it would send it to the LLM for analysis.
To figure out what to do.
Yeah, and in this case, the malicious reply had that transfer instruction.
Right.
And the LLM thought it was a real command.
And it didn't realize it was bad.
It didn't realize, no.
Wow, so they explored some defenses, right?
They did, yeah.
What did they look at?
So they looked at two main strategies. The first one was to just limit the functionality in the plugins.
Okay, so like make it so it can't send funds at all.
Exactly.
Okay.
Which would reduce the risk, but it also makes the agent less useful.
Right, it defeats the purpose a little bit.
Exactly.
Okay. And then the other one was to try to make the system more resistant to prompt injections while still keeping all the functionality.
Yeah, have your cake and eat it too.
Exactly. And how did they try to do that?
So they looked at techniques like defensive prompting, where they wrap external data in these special tags and tell the LLM to treat anything in those tags as untrusted.
So like, don't act on it?
Exactly, yeah.
And did it work?
Well, it worked for basic prompt injection attacks. But they found that it was still vulnerable to more sophisticated attacks.
Especially when you combine it with the memory stuff.
Yeah, exactly.
So let's talk more about those memory injection vulnerabilities.
Okay.
What did their experiments show?
So they found that you could actually bypass a lot of those prompt-based defenses by using what they call context anchoring.
Context anchoring, what is that?
So basically you craft these malicious requests that look like something the system would normally do.